Hey folks, let's talk about the stoichiometry of titrations. We're focusing on acid-base titrations here today, and so at the core of acid-base titrations is a neutralization reaction. And a neutralization reaction is when you react an acid with a base and you end up making water and an ionic salt. So first, let's just take a look at how you write these neutralization reactions, because from there, we can actually do the stoichiometry. The classic of all, hydrochloric acid and sodium hydroxide. These reactions are fundamentally double replacement reactions, and so we need to switch the way they're combined. And so what we're going to end up making here is water, and that water is the H and the OH combining. And then you're also going to make your ionic salt. And so this is the remaining anion and cation combining, in this case, to form NaCl, sodium chloride. So there's your neutralization reaction between hydrochloric acid and sodium hydroxide. Let's look at three more. So for this next one, I have acetic acid and potassium hydroxide. The hydrogen in the acetic acid will react with the hydroxide in the potassium hydroxide to form water. And then the remaining pieces are the acetate and the potassium ion, both of which are +1 and -1 respectively, so those charges cancel. Down below here, I've got oxalic acid, H2C2O4. This is a diprotic acid, and so typically for these titration processes, we are writing the complete neutralization reaction. I have to use up both of those hydrogens. So each hydrogen requires its own hydroxide in order to react. We are still making water. It's just that you're going to need two hydroxides because you had two hydrogens. And so you'll combine the hydrogen and hydroxide to make water. And then you will be looking at what's left over, which is the oxalate and the sodium. So you get sodium, you get oxalate. Charge-wise here, you all know that sodium is +1, oxalate's -2. And so you'll need two of the sodiums, which is useful. And so the final balanced equation here is H2C2O4 plus 2 NaOHs makes 2 H2O plus the Na2C2O4. Please note, and remember we've talked about this before, as you do these double replacement reactions, your subscripts may change from left to right because those subscripts are there to balance the charges in the compounds that you're working with. We have kind of the opposite option down below with our last example. Here I have a monoprotic acid and a dibasic base. So I've got calcium hydroxide, which has two hydroxides. Again, you always make water, and the water is an H and one OH, so you're going to need two of those acids. You'll end up making two waters, and then you're going to end up with calcium iodide, and calcium iodide is CaI2. Calcium has a +2 charge, iodide has a -1 charge, so you need those subscripts. So just like with every stoichiometry problem, the first part is writing a balanced chemical equation. Once you've got that part down, it's time to actually do the titration stoichiometry problem. So what a titration is it's basically reacting an unknown solution. Maybe you don't know concentration, maybe you don't know the identity, something, you don't know something about an unknown solution with a solution that you know everything about. You know what it is, you know the concentration, you know the volume you're using. So you know everything about one solution, and that allows you to find a missing piece of information about a second solution. I'm going to look at two examples here. So first, what's the concentration of sodium hydroxide? If it took 34.5 milliliters of a 0.00980 molar hydrochloric acid solution to neutralize 25 milliliters of that base. Just like with every stoichiometry problem, start by writing a balanced chemical equation, please. These are strong acids and strong bases, so this reaction will go to completion. So I've got an arrow that goes all of the way rather than an equilibrium arrow. And we are going to generate a BCA table. Now, your BCA table needs to be in moles. We're flipping back to moles here, folks, because we're really just doing a stoichiometry problem. And so this is just a solution stoichiometry. We did these earlier this year. You've done them a bunch. We need to figure out how many moles of HCl we have, and that will allow us to figure out how many moles of sodium hydroxide were present. So initially, once you've figured out the moles of hydrochloric acid using your molarity equation, we know that all of the hydrochloric acid reacts. This is the kicker with a titration, is we're assuming that all of the reaction occurs, and it occurs like we let the reaction go just until completion and then we stop it. So these values refer to the instant that the reaction is completed. And then once you know what's going on with the HCl, then you know about the sodium hydroxide. Because this is a 1-to-1 mole ratio, I can write the amount of sodium hydroxide that must have reacted. And again, since we're going just to completion, I know I must not have any of that left over, which allows me to figure out the amount of sodium hydroxide that I had to start with in moles. So now I know the moles of sodium hydroxide that was present in that solution, and I know the volume of that solution. So I have everything I need in order to calculate the molarity of my sodium hydroxide. I'll take my moles, and I will divide this by the liters of sodium hydroxide that were present. So of course we're converting from milliliters to liters. And this gives a final answer that is 1.35 times 10 to the negative second for your molarity. So this is kind of in regular looking things, 0.0135 molar for my solution's concentration. So it's easy and often used to calculate the concentration of an unknown solution. We can also use titration stoichiometry to predict what volume of a chemical of a solution would be needed to react. So in this case, I've got 0.122 molar nitric acid. I'm reacting it with 20 milliliters of barium hydroxide. And the question is, what volume am I going to use? As with every stoichiometry problem, we need to start out with a balanced chemical equation. And for this one, barium hydroxide is dibasic. Its formula is BaOH2. And so that means I'll need 2 moles of the nitric acid as I am reacting this, because I need to make 2 waters. And then I'll make barium nitrate. Again, BCA table. So once you have your BCA table, you are ready to figure out for the chemical you know both a concentration and a molarity for, how many moles that represents. First off, I figured out my moles of the barium hydroxide because that's the chemical I know both the molarity and the volume for. And so that tells me how much barium hydroxide was reacting. And then of course we're going just to completion. So I will use all of this up, have none left over, and that tells me how much nitric acid reacted. Since I know, again, I had to get just to the point of reaction, so the stoichiometric equivalence of these 2 different chemicals. And so I know the amount of nitric acid that was present originally. And so then if I need to figure out what my volume was, I know molarity is moles over liters, and therefore the liters, the volume, will be the number of moles divided by that molarity for the nitric acid. And so that is 0.0820 liters, or in milliliters, 82 milliliters. And so this is a really nice way in order to figure out the amount of a missing material or amount of an unknown material, be it the concentration, be it the volume, or the moles of whatever it is.